All right, today we're jumping into the physics of, well, pretty much everything that moves. We're talking about kinetic energy, the fundamental energy of motion. Let's get right into it.
So what do these three things have in common? It kind of sounds like the beginning of a weird joke, doesn't it? But it's actually a fantastic physics question. They're all perfect examples of kinetic energy in action, and by the time we're done here, you'll see exactly how they're all connected.
Okay, so first things first, let's get a really clear idea of what we're actually talking about here. What exactly is kinetic energy?
To put it simply, if something's moving, it has kinetic energy. That's it. It's the energy an object picks up as it gets going. You see, to get something to move from a standstill, you have to do some work on it, and that work transforms into this energy of motion.
Now, an object's kinetic energy really boils down to two key ingredients. First up is its mass, basically how much stuff it's made of. And the second thing is its velocity, how fast it's moving. Let's see how these two work together. So, picture this. A huge truck and a tiny little car are both cruising down the highway at the exact same speed. Which one has more kinetic energy? It's gotta be the truck. Because it has so much more mass, it packs a much bigger energetic punch, even when they're going the same speed.
Okay, now let's flip that scenario. Imagine we have two cars that are exactly the same, so their mass is identical. But one of them is just flying down the road way faster than the other. It's no surprise that the faster car has more kinetic energy. But what's really fascinating is how much more. And that brings us to the recipe.
So let's actually look under the hood at the recipe for this energy, because this is where we find the secret ingredient that makes speed so unbelievably important.
And here it is. The formula seems simple enough, right? Kinetic energy equals 1/2 times the mass times the velocity squared. So m is mass, v is velocity. But you see that little 2 next to the v? That's the game changer. That one little number changes everything.
So this is absolutely the key takeaway. Kinetic energy doesn't just go up with speed, it goes up with the square of the speed. This means if you double an object's speed, you don't just get double the energy, you get 4 times the energy. It's why velocity has a way bigger impact on an object's kinetic energy than its mass does.
Okay, this is where it all clicks. Just check this out. Let's say we have body Y. That's our baseline. Now look at body X. We've doubled its mass. So you're thinking, okay, more mass, more energy, right? But we cut its velocity in half. And because that velocity term is squared, having the speed doesn't just cut its contribution in half, it cuts it down to 1/4. And the final result? Even with twice the mass, body X has only half the kinetic energy. It's just a brilliant illustration of how dominant speed is in this equation.
Kinetic energy doesn't just exist on its own. It's actually part of a dynamic duo. So let's meet its partner, potential energy.
Potential energy is basically stored up energy. It's the energy of what could happen. Think about a rock just sitting at the top of a hill, or the water being held back by a dam. It's not moving yet, but it sure has the potential to. And here you can really see the difference side by side. Potential energy is all about its position. It depends on mass and height. Kinetic energy is all about motion. It depends on mass and velocity. They're really just two sides of the same coin.
And that coin is called mechanical energy. Now, in what we call a closed system, which basically means no outside forces like friction are messing things up, the total amount of this energy stays the same. It's not created, it's not destroyed, it just transforms from potential to kinetic and then right back again.
A pendulum is the absolute perfect example of this little energy dance. At the very top of its swing, it stops for just a split second. At that moment, all of its energy is potential. Then, as it swings down, that potential energy gets converted into kinetic energy. It hits its maximum speed and maximum kinetic energy at the very bottom. And then, as it swings up the other side, that kinetic energy gets turned right back into potential. It's this constant, graceful transformation. So, this whole energy dance thing isn't just a concept from a physics book. It is happening all around us, all the time. And we've gotten really good at putting it to work. I mean, just think about it. Wind is just air in motion, and we capture its kinetic energy to spin turbines. Hydroelectric dams take all that stored potential energy from the water and convert it to kinetic energy to generate power. A wrecking ball is, well, a pretty brutal application of kinetic energy. And even you, when you walk or run, your body is a little machine that's converting chemical energy from your food into the kinetic energy of movement.
Now, as a final little thought on the science, our classic formula works perfectly for cars, planets, you name it, but when things get really, really fast, I'm talking close to the speed of light, we have to bring in Einstein. This formula here shows that as an object is closer to the speed of light, its kinetic energy starts shooting up toward infinity. It's a fascinating, mind-bending topic for another day.
So I'll leave you with a question to chew on. We know energy is conserved, right? It's never destroyed. So when you're out for a run, you have a lot of kinetic energy. And when you stop, it's zero. That energy didn't just vanish into thin air. So where did it go? It's a great reminder that these fundamental laws of the universe are at work in every single moment of our lives.